In this video, we'll discuss static error constants. When a control system excited with the static input signal and then the steady state input may be zero, constant or infinite. When a control system excited with the static input signal, then the steady state may be zero, constant or infinity. For type 0 system, will have a constant steady state error when the input is a step signal. For type 0, that is when n is equal to 0, type 0 system will have a constant steady state error, that is ESS. ESS will be constant when the input is a step signal. For type 1 system, will have a constant steady state error, that is ESS will be constant when the input is ramp signal. For type 2 system, we'll have a constant steady state error when the input is parabolic signal or acceleration signal. So, for type 0 system, the steady state error ESS will be constant when the input is unit or a step input, step signal. Type 1 system, the steady state error will be constant when the input is ramp signal. For type 2 system, steady state error will be constant when the input is parabolic signal. Then for the three cases mentioned, the steady state error is associated with one of the component defined as follows. So that is positional error constant, that is defined by Kp is equal to limit s tends to 0 g of s into h of s. Positional error constant is equal to Kp and that is equal to limit s tends to 0 g of s h of s. Velocity error constants, that is Kv is equal to limit s tends to 0 s into g of s into h of s. Acceleration error constants is Ka is equal to limit s tends to 0 s square g of s h of s. For type 0 system, Kp. For type 1 system, it is defined by Kv, and type 2 system, it is Ka. So that is that type is defined by the value of s. In the first term, Kp is equal to limit s tends to 0 g of s h of s. Here s to the power 0. S term is not there, so it is s to the power 0. I can write, so it is 1. So it is type 0 system. In the second, velocity error constant Kv, limit s tends to 0 s to the power 1 g of s h of s. Here s to the power 1, so n is 1, so it is type 1 system. For acceleration error constants is defined by Ke, it is limit s tends to 0 s to the power 2 g of s h of s. So s to the power n is 2, so type 2 system. So next, steady state error when the input is unit step signal. So we'll find out now steady state error when the input is unit step signal. We know that steady state error ESS will be given by limit s tends to 0 s into r of s divided by 1 plus g of s into h of s. And this is for type 1 system. And when the input is unit step input, r of s is equal to 1 by s. So I can write ESS is equal to limit s tends to 0 s into r of s is 1 by s divided by 1 plus g of s h of s is equal to limit s tends to 0. I can cancel this s term. So I will get in the numerator 1 divided by 1 plus g of s h of s. So finally, therefore I can write ESS is equal to limit s tends to 0 1 divided by 1 plus kp, where Kp is equal to limit s tends to 0 g of s into h of s. So I have written just limit s tends to 0 g of s h of s as Kp. For type 0 system, Kp is equal to limit s tends to 0 g of s h of s. So I can write limit s tends to 0 k into, I can write s plus z1 into s plus z2 s plus z3 divided by s plus p1 s plus p2 s plus p3, or limit s tends to 0 k into, I can write because it is type 0 system, s is equal to 0, z1 z2 z3 will get denominator also in the place of s, just substitute 0, will get p1 p2 p3. So finally, it is equal to constant k into z1, z2, z3 in the numerator divided by p1, p2, p3 wholes in the denominator. And I can say it is a constant. So ESS is equal to 1 divided by 1 plus Kp is equal to constant. For type 0 system, it is steady state error, ESS will be constant. Just in the previous discussion, we told that for type 0 system, the steady state error will be constant if the input is unit step input. Now we proved that one here. Next, steady state error with the unit step input or 0 system. For type 1 system, Kp is equal to limit s tends to 0, k into numerator 0 plus z1 into 0 plus z2 into 0 plus z3 divided by s into 0 plus p1. It is, see, Kp is equal to limit s tends to 0, k into 0 plus z1 and 0 plus z2, 0 plus z3 divided by s into, uh, our equation is s into s plus p1, s plus p2, s plus p3, right? Here s is where it is equal to 0, right? So denominator is 0 into 0 plus p1 into 0 plus p2, 0 plus p3. So finally I will get here after this simplification k divided by 0, because s term is there in the denominator, it is type 1 system, so k divided by 0 is infinity. So therefore steady state error ess is equal to, for type 1 system, it is 1 divided by 1 plus 1 plus limit s tends to 0 s into g of s h of s, so it is infinity. So 1 divided by 1 plus kp is infinity, so it is, we will get it is equal to 1 divided by infinity is 0. So ESS will be 0 for type 1 system. For type 2 system, it is k divided by s square. Steady state error where the input is ramp signal. So ESS is equal to limit s tends to 0, s into r of s divided by 1 plus g of s h of s. Because for type 2 system, it is in, yeah, steady state error when the input is ramp signal. It is s into r of s divided by 1 plus g of s h of s. Input is ramp means 1 divided by s square, r of s is equal to 1 divided by s square. So I can write ESS is equal to limit s tends to 0, s into 1 divided by s square divided by 1 plus g of s h of s. After the simplification, I will get 1 divided by s in s plus s into g into s plus h of s, s into h of s. So I can write this one as ESS is equal to limit s tends to 0 is into 1 divided by s plus kv. So finally, error signal ESS is equal to 1 divided by kV, where kV is the velocity constant and it is limit s tends to 0, s into g of s h of s, velocity time constant. So in the next concept, in the next video, we'll discuss its values for type 0 system, type 1 system, type 2 system for kV.